Hello everyone, a very good afternoon to everyone present here today. My name is Lee and I will be presenting on my title, A Study on Thickness Retrieval for Saline Ice using a Radiative Transfer Inverse Scattering Model with Simulated Annealing. This is a summary of my presentation today. I will start off with the introduction, followed by the objectives of the research, and then a little bit on the background of the inverse model that is being developed, the methodology of the current work and the results, followed by a conclusion and the recommendations on future work. So remote sensing has been applied in many areas, such as urban planning, oil spill management, forestry management, etc. And one area that we are looking at is how we can apply remote sensing to sea ice research. In sea ice research, scientists are interested in how they can perform year-long monitoring of the sea ice formation, how they can collect the data of the physical properties of the sea ice in the long term, how they can access information from remote areas in the polar regions. So these are some of the challenges faced by researchers who are doing sea ice research. And remote sensing actually offers one option or possible solution, okay, for them to perform all these challenges. So the development of a forward and inverse model is important if we are looking at how we want to apply remote sensing to sea ice. So in today's presentation, the main objective is to present on an alternative solution to a previously developed inverse model, and to present on the latest test results using both single and multi-polarization radar backscatter data. So this is the background of the current inverse model. So it is based on the previously developed inverse model known as the Radiative Transfer Inverse Scattering Model, which itself is based loosely on the Radiative Transfer Thermodynamic Model for sea ice thickness retrieval from time series scattering data proposed by Shi. So the previous model consists of two portions: an improved radiative transfer forward model incorporating the dense medium phase and amplitude correction theory and the Leverberg-Marquardt algorithm. In terms of the optimizer, the limitations of the LMA is it is a local optimizer which increases the likelihood of being trapped in the local optima. And the inverse model is not generalized because when we apply LMA, we need to calculate the Jacobian matrix. So if we want to extend the model to other applications, we need to recalculate the Jacobian matrix with respect to the problem function. So in the current work presented today, we are proposing to replace the LMA with a simulated annealing. So SA is a global optimizer which improves the convergence because it is less likely to be trapped in the local extremum. And because it does not require calculating the Jacobian matrices of the problem function, it becomes more generalized and it's easier for us to extend the model to other applications. So this is the flow chart of the inverse model. So we input the physical parameters of the sea ice or saline ice, including the gas thickness, into the forward model. The SA will be used to compare between the predicted backscatter data from the forward model and the actual backscatter data, which comes from measurement sources. Okay, and it will then calculate the error function between these two. And if the global optimum is not reached, it will adjust the thickness. Okay, and recalculate everything. Okay, until the global optimum is achieved. So the sea ice thickness where the SA is able to achieve the global optimum will be given as the output of the inverse retrieval, okay, and is given as the predicted sea ice thickness. So this is the configuration for the forward model. At the moment, we are only employing a single layer forward model. Okay, so we have the sea ice layer sandwiched between the air layer at the top and the ocean layer at the bottom. And embedded in the sea ice layer are spherical shaped scatterers. So this is the formulation of the radiative transfer theory. And the improvement made here is in the phase matrix, okay, where we apply the dense medium phase correction factor, okay, to take into account the close spacing effect among the scatterers. So in our CIs, we treat the CIs as an electrically dense medium. Now the simulated annealing optimizer is a global optimizer which explores the function's entire parameter space before the optimization. And this optimizer is based on thermodynamics, which is the study of a system's thermal energy, especially how we can cool and anneal a metal. Now in metallurgy, annealing is a technique where it involves heating and controlled cooling of a material in order to increase the size of the crystal and reduce the defects. Thus, it is able to achieve a far more stable state. The advantage of using the SA is it is independent of the starting values. It is capable of escaping from the local optima to find the global minimum. It has less stringent assumptions, and this allows the SA to be able to deal better with functions with bridges and plataus. And it is capable of optimizing functions not defined for some parameter values. The SA algorithm applied in the model is based on the algorithm by Goff. So this is the error function that we are seeking to optimize, which is the error difference between the predicted radar backscatter data from the form model and the measured backscatter data, which can be from the satellite image or other measurement sources. So we, as mentioned earlier, we perform the optimization by varying the CI thickness, and the CI thickness that achieves the global minimum is the predicted CI thickness. So in our research work today, we are looking at applying the inverse model on retrieving saline ice thickness from the parameters performed using the parameters measured during the Serialex 93 experiment as reported in Yeong et al. So these are the parameters that we extracted from the paper. Okay. So first we perform a sensitivity analysis using the forward model, for 25 degrees and 30 degrees, since both incidence angles are given in the Yeong et al. Paper. So we find that the forward model is able to achieve a trend as we calculate the VV and HH radar backscatter data using the measured physical saline ice properties, from the paper. The only exception or the only case that is important here is the measurement at 3.5 centimeters. So you will find that for this particular case, the calculated output from the forward model, is both lower compared to the measured values. It is also the same for 30 degrees. But for both incidence angles and for all the polarization, we are able to achieve a similar trend. This is the retrieval result of the saline ice thickness using the data from Yeong. So majority of the results appear to give a good agreement within 3 centimeters. And the retrieval result using multi-polarization data, which is in this graph, is the colored one, appears to give a better agreement compared to single polarization radar backscatter data. Now the test number 2, which corresponds to saline ice thickness 3.5 centimeter, is not as good as the other cases, as I mentioned earlier, because the calculated radar backscatter data from the forward model is lower compared to the measured radar backscatter data, reported in the paper. Lastly, the results at 30 degrees appears to give a better result compared to 25 degrees. So limitations of the model is the accuracy of the retrieval depends on the accuracy of the forward model. The shape of the scatterer currently is catered for spherical, but the actual shape of the scatterers reported in the paper is ellipsoidal. So this may affect the accuracy of the forward model prediction. The prediction is less accurate if a saturation occurs. And lastly, we did not include cross-polarization data because currently for our model, the prediction is not so accurate. As a conclusion, we have further verified the inverse model that integrates RT-DMPAC and SA and applied it to saline ice thickness retrieval. So the results show that the retrieval of the thickness is possible The use of multi-polarization data improves the accuracy of the retrieval compared to single polarization data, and the results for 30 degrees is better compared to 25 degrees. So as a possible future work, we may want to look at extending the model to retrieve other CI's physical parameters, to improve on the form model by allowing it to cater for ellipsoidal or arbitrarily shaped spectrals, to extend it to multi-layer configuration, or to extend it to multiple surface scattering to improve on the cross-polarization radar backscatter data prediction. With that, I'd like to thank you for your attention, and I will conclude my presentation for today.